Let's look at a kind of tricky continuity problem. Usually I've been giving you a function and asking you to find the points where the function might be discontinuous. But now I'm giving you a graph and asking you to create a possible function. So I'm seeing 4 places where this function is not continuous. I'm seeing an asymptote at -1. I'm seeing an asymptote at x equals 2. And I'm seeing a removable or point discontinuity at x equals 1. And I'm seeing another removable discontinuity at x equals 4. So let's think about what would create these. So let's look at this asymptote. This asymptote exists where x equals -1. That means when I plug -1 into this function, I will get a 0 in the denominator. Well, that means I must have a factor of x plus 1 in the denominator, because when I plug in a -1, that's going to give me a 0. Boom. Let's go to my next asymptote. This says this function does not exist when x equals 2. That means when I plug in 2 into my denominator, I'm going to get a 0. Well, a factor of x minus 2 will accomplish that. 2 minus 2, 0. Removable discontinuities, also called point discontinuities. This is happening at x equals 1. If you recall, we get those little point or removable discontinuities when you have a factor in the numerator and in the denominator that divide out. So let's see. If I have an x minus 1, that's going to create a 0 in the denominator. And if I put an x minus 1 in the numerator, those would then cancel each other out. You're kind of getting rid of the asymptote, but you're still left with a little tiny hole. Here we have a removable discontinuity at x equals 4. That comes from a factor of x minus 4. And again, since it's removable, you need to have the factor in the numerator and in the denominator. So here's a possible function that would create that graph. All right, let's look at this last problem too, because the directions on this are a little tricky. There's a total of two discontinuities in these piecewise functions below. Identify the function and the type and location of each discontinuity. Okay, a total of 2. So maybe both discontinuities are here. Maybe both discontinuities are here. Maybe there's one in each. So let's dive on in. Okay. These are each piecewise functions. Piecewise functions are tricky because you have to look for all 3 types of discontinuity. Of course, with piecewise functions, you need to make sure that one piece ends at the same exact y value where the other piece begins. If they don't, you have a jump. You also have to look inside of each piece to make sure you don't have any asymptotes or any removable discontinuities. Let's just look for jump first. This first piece ends at x equals 0. Let's plug in the 0 and see what the y value is. -3 divided by -3 is 1. So this piece ends at the point 0, 1. This piece begins at x equals 0. Plug in the 0, 3 divided by 3. Oh! This piece ends at 0, 1. This piece begins at 0, 1. No jump. Let's look over here. Isn't it going to be the same? Let's see. When I plug in a 0, 1. When I plug in a 0, 1. No jump. Okay, so I'm going to just get rid of my jump option. There's no jump in either one of these. Okay? So far, so good. So now I have to look at each individual piece. So I'm looking here, ooh, x minus 3. What do I have to avoid? I have to avoid 3 because 3 would give me a 0 in the denominator. But this is tricky. Now I have to look at my domain. This domain tells me when I'm on this piece. So I'm not going to try to graph this function, but let's just say, I don't know if this helps at all. Let's say this is my green This is my green function, and this is my red function. So this domain says I'm on the green function, green function, green function, green function, green function, until I get to 0. And then I'm on the red function, red function, red function, red function. I'm not saying these look like that. But this green function, this green piece, is going to have a problem when x is 3. But when x is 3, I am safely on this red piece. I'm not on this piece when x is 3, so I don't have a problem. Now let's look at this red piece. I'm going to have a problem when x is -3, because that creates 0 in the denominator. Well, -3 is down here. I'm not on this red piece when x is -3, so I don't have any problem at all. This is going to be a nice, flowing, continuous function. No asymptotes, no holes. So it looks like all of my discontinuities are going to happen in function 2. So I'm going to put function 2. So let's do kind of the same scenario here. And again, I'm not pretending that I'm graphing the function, but let's just say this is my blue function, and that blue function is for all x less than 0. Let's say this is my purple function for all x greater than 0. This denominator is going to give me 0 when x is -3. When x is -3, whoops, my color coding is off. When x is -3, I'm on that blue piece. -3 is in this domain. That means I have a problem when x is -3. What kind of problem? I have an infinite discontinuity. Remember, infinite is the same as asymptotic. I don't care which word you use. Infinite or asymptotic, that's going to be an asymptote at -3. Same thing here. When x is 3, I'm going to have a 0 in the denominator. When x is 3, I'm on that piece. That's a problem. I'm going to have another asymptote when x is 3. It's also going to be infinite or asymptotic. And the reason neither one of those is removable, I'd have to have the same numerator as denominator, cross those off. Or I'd have to have that same factor up there. Those were 2 tricky problems. I hope this helped. Have fun.